As we start talking about double displacement reactions and solubility, I'm going to ask you to have your pause finger ready to go, because there's a few points where we're going to have to pause, probably zoom in on something, take a really good look at things, because it's going to be learning how to read a table. So double displacement reaction, we know what this looks like. We know what the pattern is. However, I really want you to pay a bit more attention to how it works, because we sometimes get things turned around. So I've got a metal nonmetal with another metal nonmetal, and the two metals are going to trade places. Okay, so in other words, the first element is still going to be the first element. So if it's first element written down as a reactant, it's going to be the first element written down, at least in the pair. It doesn't have to be in the order left to right kind of thing, but within that pair, so it's AD, not the other way around. I'm also not going to put two metals together. That makes no sense at all. The charges are not going to change. So if I have iron, for example, it's not one of my always this plus whatever in a compound, whatever the charge is for the metal on the reactant side, it stays exactly the same charge on the product side. And when we're predicting the products, that actually becomes really useful to know, because charges matter. Okay, for example, in something like this, so if I have this one here, copper has, I know chlorine is a -1 charge each, so that means copper is a +2. I know the sulfur is a -2 each, that means that iron is a +3 rather. They are going to maintain those charges as they go to the other side. Too easy. Okay, follows the same pattern where AB, BC, or CD, and so on. Okay, going to take a little side trip for a second. If an ionic compound dissolves into water, it exists as ions. If it does not dissolve, it will be a solid in that water. You can mix it with water, this will not dissolve. Okay, so all ionic compounds are solid at room temperature. If I add them to water, some will dissolve, some will not. If they do not dissolve, they exist as solids. If they are if they do dissolve into the water, they will exist as separated ions. We'll come back to that another time. There are certain ionic compounds that do not dissolve in water, and they will have a low solubility. Too easy. So we talk about high solubility, we talk about low solubility. Low solubility is not the same thing as no solubility, but for our purposes, we're going to kind of treat it like that. Okay, low solubility compounds will have low solubility, which means you put them into water, they don't mix. They stay as a solid. They stay kind of powdery in some cases, and then they just make a mess of the whole thing. I'll show you a picture of that a little bit later. Okay, important though, it's got to be within water. All right, too easy. I can also have them in water as a product of a chemical reaction, of a double displacement reaction, which is why we're putting those two things together, double displacement and solubility. Okay, this table, pause it to look at it. Now, I do need to talk about it for briefly. There is a top section is where it says these compounds are very soluble. So if I look at the middle column there where it says ion, those are all the negative bonding partners. And typically, anything with a NO3 is going to be soluble. Anything with a Cl or the other halogens, bromine, iodine, those are going to be soluble. Then there's the exceptions. So for example, if I look at chloride, I should say, all compounds of chloride are soluble except copper 1+, silver 1+, mercury 2+, although it's a bit weird, and then lead 2+. Everything else is soluble. Those are the exceptions. If I go to the bottom where it says slightly soluble, those are the ones that have very low solubility. So the first one, CO3 with a 2- charge, almost nothing is soluble if that is the negative bonding partner, except group 1 compounds. Sodium, for example, lithium, potassium. That's how we read that table. We'll get some practice with that. Okay, so speaking of practice with that, this compound here, iron with chlorine. So iron 3 chloride, if we've done the nomenclature. Go back to my table, I find the chloride. I look for, it's organized according to the negative bonding partner, I look for the chloride. There it is at the top. And then I look for iron. Iron is not listed as an exception, which means it must follow the high solubility pattern. Okay, so that thing has high solubility. But if I look for copper with OH, okay, I go looking for OH. Oh, there it is near the bottom. Those compounds of OH are typically not soluble, or typically are slightly soluble, typically have low solubility. Then I'm looking for the copper. I don't see it in my list. That means it follows the pattern of low solubility. I can look for SO4 with iron, and SO4 is near the top, and I'm looking for iron. It's not listed, so it must also then be high solubility. That's how it works. It's actually really easy once you know how to read it. Okay, if I go back to a double displacement reaction where I'm predicting products and then I'm looking at the products. This one here. By the way, if you were to look for these compounds on that table, you would find that both of the reactants have high solubility, which is normal, okay? But the products might be a different story. The products, if I want to look at the products, well, now I'm only looking at the products. So I have the OH. OH is down there near the bottom. I don't see iron listed, so it follows a slightly soluble pattern. And the sodium one, if I look for it, it's going to follow the pattern. So in other words, sodium Na with NO3, that is going to follow the high solubility pattern, and the OH will follow the OH low solubility pattern. So now what do I have? Well, now I've got this combination of one that dissolves quite well and one that doesn't. But don't forget, they are in the same container. They are mixed together. So what I'm going to see is that one thing is clouding up everything. That thing that does not dissolve, that solid that I produced, that solid product, is the very definition of what's called a precipitate. Precipitate is a solid product of a chemical reaction. Only and always the product. Not every reaction has one, but if it does have one, it will be the product. Okay? That is going to cloud up the whole thing. I never have to worry about, well, which one and will it, because if there's a precipitate, if there's one that has low solubility, cloudy precipitate. Okay? And then what I'm going to see is something that looks like that. Now, if you look at the solutions, right, the one that's pouring in and the other one, where they are not mixing, clear and colorless. They're solutions. Where they are mixing, the whole thing is going cloudy. Precipitate. Eventually that precipitate will settle out to the bottom, but that's a solid in there. Okay, I'm going to get you to use the table again. You may need to pause, you may need to write this down and predict which ones have precipitates. And then you're going to go to this table to do that, and then we'll come back to the answer after you paused it and figured it out for yourself, but we'll double check on the answers here. First one has a precipitate with the silver. Second one has a precipitate with the barium and the CO3, and the last one has a precipitate with the iron and the OH. Okay, that's it. That's really all there is to it. Reading that table and predicting products. Now, sometimes there are metals that have more than one possible charge, and one of them is on the list of exceptions and the other one is not. That one's going to be tricky. Well, it's not hard. We just have to be paying attention to it. Anyway, that's all there is to it. Talk to you another time.